Okay, let's jump right into this explainer. When we talk about building massive, trillion-parameter artificial intelligence models, there's this really common assumption that we just scrape the internet, feed it to a supercomputer, and out pops a genius AI. But the reality, raw web data is essentially dirty river water. It is absolutely full of pollutants. Before it can ever be used to power these incredible systems, it has to be aggressively purified through a massive filtration assembly line. So today, we're going to explore exactly how that purification process works.
This quote right here flips a huge misconception completely on its head. A lot of people think, the bigger the model or the more compute power you throw at it, the better it gets. But sheer compute power literally doesn't matter if you're feeding your model absolute garbage. High-quality data is the true foundation. It's the single largest determinant of performance. When you get a brilliant answer from a tool like ChatGPT, it's not just because the computer is big, it's because of the incredibly clean diet it was fed. A clean diet means the model generalizes better, hallucinates less, and learns much, much faster.
What we are constantly fighting against is systematic noise. We're talking massive amounts of duplicated content, total gibberish, toxic filler, and even adversarial injections designed specifically to break the models. This isn't just a typo here or there. If we don't catch this systematic noise early on, the AI models actually spend their massive computational capacity memorizing junk instead of learning the useful, underlying structures of human language. They basically hit a bottleneck where throwing more compute at them is just a waste of time and money.
So, to map out how we solve this, we're going to cover why data quality rules all, the first pass using heuristics and rules, deep evaluation with LLMs and humans, catching outliers and safety risks, the final deduplication polish, and then we'll look at the complete filtering pipeline.
Okay, let's dive into that first pass, heuristics and rules.
When you're staring down billions of documents and trillions of tokens from places like Common Crawl, you obviously can't read them all. You have to rely on blazing fast statistical math. Think of these as the giant, shallow grates at the very beginning of our water filtration system. We use simple length checks to drop anything under 5 tokens or over 2,000 to instantly remove useless stubs or runaway text. We look at the character ratio to nuke emoji spam, and we use Shannon entropy and perplexity scores to mathematically catch garbled gibberish or repetitive boilerplate. This math scrubs away millions of bad documents in a flash before they ever get near the model.
To handle labeled data early on, we use a brilliant mathematical trick called the complexity gap, or CG score. It essentially estimates how much actual information a label gives to a piece of data. It does this by comparing the mathematical complexity of a real pair against one where the labels are totally randomized. High CG, the label makes sense. Low or negative CG, it's probably noisy or just wrong. This lets us detect bad labels without ever having to train a model to check it, which is incredibly efficient.
Moving deeper, we hit deep evaluation with LLMs and humans.
Those shallow heuristics we just talked about are incredibly fast, but honestly, they're pretty dumb. They can't tell if a paragraph actually makes logical sense or answers an instruction correctly. So we step up to LLM as a judge. We literally use modern advanced language models, like GPT-4 or Claude, to read and rate the remaining content on highly structured rubrics. This scales massively and lets us measure complex, nuanced properties of the data that simple math completely misses.
And the AI judge isn't just giving a simple thumbs up or thumbs down. It strictly evaluates data across dimensions like fluency, coherence, and factuality. Is the text well-formed? Does it flow logically? Is it actually true? The LLM scores the data from 1 to 5 on these specific traits, creating a structured quality score for every single piece of data. If a piece of text bombs its factuality or safety score, it gets dropped from the pipeline immediately.
But we can't just hand the keys entirely to the machines, right? Because LLMs still hallucinate their own judgments. Humans remain the absolute gold standard. Think of human evaluators as the microscopic purifiers for high-stakes data. They step in to evaluate small, critical samples to calibrate the LLM judges and make sure they are scoring accurately. Humans are essential for navigating those tricky ethical contexts that an AI just might not fully grasp yet.
Next up is catching outliers and safety risks. Even after all that filtering, really strange adversarial data still sneaks through. So we extract vector embeddings, which basically turns text into mathematical coordinates in a high-dimensional space. Then we compress that down and use clustering algorithms to literally visualize the data. Normal, good data clusters together in these big, dense continents. But poisoned or weird data, it forms these isolated, sparse little islands floating out in nowhere,
Once we spot an outlier island, boom, we immediately cut it out of the dataset.
Beyond the data itself, we also have to evaluate safety behavior. This is where we hit a super delicate seesaw between two errors: overpunting and underpunting. We desperately want to avoid underpunting, which is when the model incorrectly answers a truly toxic prompt. But if we swing too far the other way and overpunt, the model gets overly cautious and starts refusing perfectly normal, safe requests. So the whole game is balancing this trade-off. Through really careful data curation, we want to push underpunting down to absolute zero. But at the exact same time, we have to keep the overpunting rate strictly under 5%. If we go over that 5% threshold, the AI becomes incredibly annoying to use. It refuses safe requests and completely destroys the tool's utility. Threading that needle is absolutely crucial.
And that brings us to the final polish, deduplication. Now you might be thinking, wait, shouldn't removing duplicates happen at the very beginning? It's a great question, but we actually save deduplication for last because it requires massive, incredibly expensive compute. If we did it first, we'd waste an unbelievable amount of supercomputer resources finding duplicates of low-quality spam that our early math rules were going to throw away anyway. By doing it last, we ensure we're only spending that kind of money to deduplicate pristine, high-value content.
And we aren't just looking for exact copy-pasted text. We're looking for near duplicates, like heavily paraphrased text or overlapping code. To do this at scale, we use advanced tools like locality-sensitive hashing. This lets us search through billions of high-dimensional embeddings at warp speed to cluster and remove redundant content. It guarantees our final dataset is wonderfully diverse, preventing the model from just memorizing repeated information.
Let's put it all together and look at the complete filtering pipeline.
Here is the entire assembly line in full. We start at the top with the shallow grates, heuristics, and compliance to catch the obvious spam and illegal content. Then we move to outlier island detection, cutting out the weird adversarial clusters. Step 3 brings in the deep semantic reading with LLM as a judge and human calibration for factuality. And finally, stage 4, deduplication, squeezing out any redundancy. This brutal funnel ensures that out of billions of raw internet pages, only the absolute most pristine data ever touches the training algorithms.
And before any piece of data is officially approved, it receives a final weighted quality score. A full 20% is dedicated to factuality and another 20% to strict safety. Even if a document is a beautiful, flawlessly written masterpiece, if it fails those hard thresholds for safety or correctness, it is completely rejected. It absolutely has to pass this gauntlet to survive.
Which brings us to a really fascinating problem for the future. As these models grow exponentially hungrier for data, we are rapidly running out of fresh, clean, human-generated text on the internet. We're increasingly relying on LLMs themselves to generate and filter synthetic data. So the big question to take away from this explainer is, as we run out of human data, who exactly will filter the AI that filters the AI? It's a wild loop, and data filtering is absolutely going to be the frontier of artificial intelligence for the next decade. Thanks for joining me on this deep dive.